Okay, this is a walkthrough of the second section of Chapter 17, which is all about how things move through electric fields. And the analogy from the picture is that it's very, very similar to gravity or gravitational fields, with a slight difference. So, the main bit is actually, when we start thinking about fields, how they move is all about what's happening in a force. So if we go for the basic idea, we've got a field, we have some sort of strength. In this case, that field strength is uniform, it's nice and steady, and it's flowing from our positive to our negative. So we've got our direction of our field because it's a vector. Then how the charge moves through that field depends on the force produced on it by the electric field. So the main thing is actually bringing back that key concept of the fact that the force depends on both the electric field strength itself and that second charge. So think of this as our test charge, our little q, and as it goes through it experiences a force. Now the crucial bit is that it depends on the charge itself. So we've got positive and negative, whereas with gravity we just have positive mass. So things tend to fall down, they follow the field lines with gravity, they do if it's a positive charge. Guess what? Most of the questions tend to be about electrons, and so they're negative charge. So just put that in, this is mainly about electrons that we're considering. But it could be a positive or negative ion, so it doesn't matter. The force is still the same, depends on the total charge within it. The only slight difference is you'll often see for an electron, this basically goes to more frequently called F equals E, because E is the charge on an electron. So that's the symbol tend to be used for electric charge of electrons, negative, whatever. So if you've got that, you don't forget then, you're more likely to remember that it does the opposite to, shall we say, the convention. So Franklin came up with his positive charge moving in that direction. He was wrong. We discovered electrons. They're really electrons going the other way, etc. However, it doesn't get any harder than that, okay? But this method was actually used in the discovery of the electron. So one of the main aims that I want you to come away with is this idea of how we got the charge to mass ratio of an electron. What J.J. Thomson got his Nobel Prize for was discovery of this subatomic particle, the first ever subatomic particle, which was the electron. Millikan came in and added much more to it, so we'll add into that. How did they do it? Well, basically it was at the time it was unknown how things worked, and I've got a few pictures in the lesson, so we'll have a look through that. But we thought they were rays, and we thought they came from the cathode. You could tell because the way that the rays tended to light up the other end of the glass tube that it was in, so we could tell that any rays that weren't hitting this metal electrode, this positive electrode, coming from our negative cathode end, must be coming this way rather than going the other way. Otherwise you get a shadow at the other end. However, what I realise is that you can change the brightness by turning up the supply and things like that. We now know, so this is the modern day, is that they were electrons, and we can work out things about it in terms of thinking about how much it's accelerated. Now, if we try this approach to find out the speed of things, it gets really, really tricky. You have to add in a whole load of other factors, as we shall find out. So for this bit, we'll take the normal approach, and the normal approach is work done equals change in kinetic energy. Okay, so we have an electric field from the EHT, that's what's producing the electric field across this gap, and any charges within that will gain kinetic energy as the work is done by that force on the electrons. So if we bring our maths together, what is our work done? That goes to QV. Okay, if we think about electrons, that hint of EV, electron volts. Okay, but this is in joules, just be careful. So in joules, and this is going to obviously equal the standard equation for kinetic energy. Okay, so this is really, really common. This is used in an awful lot of questions. Okay, how fast is it going? If you needed to get it to that speed, if you put the numbers in, try it, and you should be able to get an answer of 28.5 kilovolts. So to get to a third of the speed of the light, not surprisingly, you need a fairly large voltage. Okay, so you need a lot of energy. Now, what we're going to do is actually use this idea, but within about 100 years, Crook, who was a bit of a loony, again more for the lesson, made these discoveries, and he actually managed to get a rough idea for how massive these rays were. So he started to believe they weren't rays but actually were particles, and it's the same principle that we now use in all of our particle accelerators, of which we'll do in the lesson a bit more. However, and I shall demonstrate this, is that if you then start firing these electrons, or these rays as they thought at the time, these rays into electric and magnetic fields, then they start to be steered around, and you can actually do quite a lot with them. For those of us who are older, with the old TVs before they were flat screen, you're firing electrons across a void, and you stick a magnet near it and you could steer the picture around, and you could really knacker the television. So yeah, that was a clip round the ear from Mum. So what we can do, and what I'm going to demonstrate to you, is that we can actually fire, and ignore this magnetic field, we will leave this bit till later because that's an easier way of doing things. But if we have just a parallel plate here, we have our positive charge and negative charge, well, we get that electric field going down, and it'll be nice and uniform. So what we can do is we can actually work out how strong the field is quite easily, depending on the separation, and we can do that to measure the size of the force. And if we know the size of the force because of the charge, then we can work out how massive it is, because what it will do is, as you fire your electrons through, just like we got at the top, they'll all steer upwards. So by measuring the curve during the electric field, then we can actually work out how far it comes out at the end, and therefore we know its speed, etc. So I should point out, it will go nice and straight when it's not in the electric field. It's only in that section there you get the curve. Okay, so it starts curving there. As soon as it comes out, there's no force on it. It will just carry on in a nice straight line. What we've got here is, we now know it's a beam, so I'm just going to cheat ever so slightly, and we have a beam of electrons coming in at a certain velocity. Now, as we have this idea of forces here, and they're all, the field is in a constant direction, the force acting on it is always going to be constant as well. So if I just take one of these, as prepared earlier, here's our electron, unknown at the time, coming in. It has a certain velocity sideways, and just like we did with the work with gravity, except this time this example is upwards, we've got a constant velocity sideways, okay, and that brings us into the calculation of S equals ut. So a nice simple equation to make that work. However, going upwards, we have a force, and that force acting on the particle is the same all the way, because that force depends on the size of the electric field. F equals E, electric field strength, multiplied by E, the charge of an electron. We could say Q if you want to be more generic. Now that means that you also have a constant acceleration upwards. So all the way through the loop we have, through the curve rather, we have a big acceleration. Now we can measure that acceleration like we did before if we know the time it takes to move from side to side. So if we know its velocity, which we can work out from here, then we know, which we got from its voltage I should say, we know that velocity, we can put that in, and from that we can then get time to put into an equation. So I need an equation that links acceleration with time, And if you think about your Suvat equations, I've got acceleration, yep. I've got time, yep. I have the initial velocity sideways, which is 0, so u in the vertical direction, yep, equals 0. And we need one more for a Suvat equation to work. So I need v, velocity at the end. I don't even know that it's a real particle at this stage, so I can't do that, but I can work out how far it has moved upwards, just the equivalent of moving downwards in a fall, so I do know s. So what I need is the equation that contains the linear acceleration, the constant acceleration equation that has all these units in. And if you think about that, that's s equals ut plus half at squared. Okay, so I can work out if I'm measuring vertical I can get the vertical acceleration from the vertical velocity and the vertical displacement it runs, as long as I have time, and I get that from my horizontal velocity and horizontal displacement. In other words, the length of these two plates. So that's my distance along. Okay, so what I'm going to do is just label up some things to make it convenient. This I'm going to state as that's the length of my plates. Let's just call it L. Nice and simple. Capital L is a big length. Here we have our idea of our plate separation. Yep. I can measure how far it's gone up. So this is going to be my my S that we want to find out about in the, I'm going to call it the Y direction. Okay, so these we can go in X direction and so on. So we know, because the force does not change its direction, that the parabolic field due to the field gives us that that shape of field, gives us linear acceleration or constant acceleration. I should say, how do we get this? The bit above says, so it will hit a screen. For us, we've actually got a fluorescent screen in the middle so you can see the curve. They just measured the curve when it hit something at the end, when it came out of the tube. So, first job, we could say, well, S in the X direction equals ut, okay, which equals, of course, L. So that's the distance it's changing that motion in. So I'm not going to worry about distance before, work distance afterwards, just the distance where it's changing its direction. And in that time, it has gone from here down to here, or up to here. Okay, so S in the Y direction equals, from our equation we've just had up there, S equals ut, well that's 0, so I'm just going to put that, plus half at squared. Now, I'm going to simplify it even further. We don't have the acceleration, but we do know the size of the force. So I can turn that into half F over m, gives me acceleration t squared. Okay, so those two equations give us our motion in two different directions. So equation 1, equation 2, okay, and from 1 we get t equals u, you know, our initial velocity, and again if it's a vacuum the final velocity horizontally, over L. Okay, we also know that from before that F, I'll just put a big and there, and F equals E, okay, where E is the charge of an electron, but we also know from what we did before that that also happens to be equal to the voltage on the plates. Okay, so this is our PD between those, divided by distance between them. Okay, so plate separation multiplied by E. So that's my large capital E multiplied by little e. So what were we doing? What did he do? He measured the displacement, excuse me, can't spell displacement, displacement at end of the plates. Okay, and from that he managed to get SY equals, and I'll leave you to rearrange this and sort it out and check it's right. V equals U squared over 2DL squared, because it's V, V squared and stuff that needs to come in, multiplied by E over M. Okay, so from that bit, what he can do, or what he managed to do, was calculate, and he did it in other ways as well and still got the same value, so can find the specific charge, okay, I'll just put units, make it, so that's coulombs per kilogram. In other words, for every kilogram of stuff, what's this, coulombs, of electron. And basically what he found out was that was a 1,860th of the smallest known particle that existed at the time, because it was so much tighter, okay, and therefore it must have the same charge as the smallest known particle at the time, which was a hydrogen ion, which we now know of course is a proton, discovered after this, and therefore we had a particle that was a 1,860th of the mass of a proton. He discovered the first subatomic particle. So the discovery of the electron, and as I said, that basically E over M, I always get this wrong, is approximately equals 1840, okay, charge to mass ratio, so yeah, of hydrogen plus ion. Okay, I can't spell ion. God, it's the end of a long day. Equals Nobel Prize. There we go. So really quite powerful stuff, just using SUVAT, the idea of a curve and the charge on it. So he discovered the electron. Unfortunately, just moving into division there, that's not the whole story. He actually just showed that it was a much smaller specific charge than other particles, so he hadn't actually discovered the particle itself. And so we're just going to pick up on some other stuff for revision, which goes with forces as well. So as we did our revision session recently, we can bring in our last character, which is the American Millikan. And what he did was a very famous thing called the oil drop experiment. Now, the oil drop experiment was based on a slightly different mathematics. Okay. Now, before we move on, just want to make really clear. Okay. This V up here, times by the charge, or E if you prefer for an electron, that will give you the velocity, lowercase v, from the voltage, the potential difference. So this is the PD of the electrodes. Okay, down here we have the V of the plates. So I'm just going to make sure PD of plates. Now our electron gun, our thing that accelerates the electrons, is back here. This is over the source, where the source of the beam is. It is a separate voltage from these. Okay, so we are talking about two different voltages. More importantly, they'll break it up in questions if they ever ask things that are like this. But more importantly, that capital V is very different from the small case v. Make it clear in your answers. Okay? Anyway, back to this. So we need to split this up. And this is where Millikan came in with a beautifully simple experiment using exactly the same mathematics. So what he did, and again we'll show you the video in the lesson, but basically he got to work out the actual charge by simple equilibrium. Okay, and what he had was the force of gravity, or the gravitational field, mg, is going to equal the force of the electric field upwards, which is of course equal to E times E again. Okay, now he actually went slightly more depth, so we'll add a slight bit more depth in our fuller version in a second, but the basic idea was he made these when they were stationary in equilibrium. Okay, so we have, excuse me, wrong pen, force due to gravity equals the force due to the electric field, mg equals, again I'm going to split it up, voltage over times by electric charge over the distance between them. So what he did was he put a chamber, he made some tiny oil drops that he could charge up, add a value on, and he let them dribble through a small hole, not dribble, but fall through a small hole, because this is like WD-40, imagine that, so a tiny droplet spray. And then he put a battery on over a distance d, so he basically made an air capacitor here, a pair of plates with an electric field between them, and what he did was he charged them up randomly. He couldn't control that, but he fired ionizing radiation in here, so it charged up the oil droplets. They all get different sizes of charges, but he went and saw what they did. Now the problem is we can't quite see what the mg is, because these are tiny droplets. We know what g is, but we don't know the mass. So how do we get that? Well, we need to just simply go where mass equals density times volume. Okay, so we can do that because it is tiny. Now, because that's tiny, we have a very small volume that is also tiny. So what we had to do was come up with a completely different method, and this is where our work on forces comes in. What he did was, this only works when it is in equilibrium held by the electric field. If he turned the electric field off, then the drop accelerates downwards. Yeah? But it's falling through air, and so what you get is drag builds up, and so we end up with this idea here. Okay, now I should say there's a little bit more to the story, I'll add it at the end, but basically if we can measure the drag, if we know the factors of the drag, then we can find out the mass. Now drag itself comes from something called Stokes' law. You'll hear it mentioned quite a lot. It's not directly on the spec, but it does bring it in, the ideas of it in. So, what he did, let's say Millikan turned it on, made it work, great, but we don't know the mass. So what he did was he then allowed it to free fall through measured distance and the time taken to fall. Now what he does was he's in a tiny little view here, so it's finished accelerating, it's falling at a constant terminal velocity. Okay, so he's adjusting the voltage, he can make them hang in different areas for different size droplets to get this bit, but when he turns it off they all fall. But they all fall at different rates, so he's very carefully watching individual droplets and see how they're affected by the voltage as well. When he turns it off, okay, so what he found was if he knew the density and Stokes' law, then he could put it together. So let me just show you the basic idea. So at terminal velocity, as I said, we've got mg equals drag. Okay, but where do we get that drag? Drag force. I'll put in drag force. It comes from Stokes' law itself. So F drag equals 6 pi, and there's all done by mathematically from the results, nu, where this is the viscosity of the liquid, the radius, and the velocity. So if you know the terminal velocity and you know how sticky the air is, basically, the rest of it's constant. So by knowing the radius, we can bring it back to this. Now mass, of course, has radius in as well because it's to do with density, where m equals rho v equals, we all remember, rho times 4/3 pi r cubed. Okay, so we could go into more and more depth, and we can cancel out the r and so on and so forth, so we can get a fuller version. But basically, this gives us a way of finding, as I say, finding the radius of the oil. So different radii will drop at different velocities because of the different drags, etc. So long story short, what he found was that all oil drops that he looked at, it doesn't matter on the size at all, oil drops had charge, after he had charged them, that is, charges of a multiple of 1.60 times 10 to the minus 19 coulombs. So he has, with evidence, found that by charging things, he found all the charges were multiple for that. Therefore, he deduced that the electrons that had been removed, that Thomson had proved that existed as particles rather than being some random cosmic, cathode rays. He found that they were individual charged particles, and therefore he actually managed to find the multiples, because they're all multiples of that, being, is there 1 electron removed, 2 electrons, 3 electrons, etc. So here's a little bit extra that goes beyond the course, and it's actually how did Millikan get to that final answer. So he found out these values, he did it by a basics technique, so using his ideas and then obviously a very precise bit of measurement to do it. So let's just take you through the idea. I'll just keep this bit on here to start with. He fired his oil in, okay, and the oil was in tiny, tiny droplets, so semi-floating, falling slowly through air. And what he did was most of them stayed up here and some fell through the hole where he could see them through a very closely through a microscope. So he's studying tiny droplets of oil, which he can't possibly measure, but he needs to be able to do the mathematics of it so he can find out how much charge is on each oil drop, which he's done by shining in radiation. Now that's not in our picture here, but he used an alpha source to collide with the oil droplets and charge them. If you do this through a plastic tube, you get charging as well, so he did it in a kind of a bit more systematic way. So what he did was the idea that if you drop something, then as it falls because there's that fundamental force, mg. Okay? And when he had it balanced, so when he turned his electricity on, so he put a voltage across this distance here, then he could get it to balance using the electric field. Okay, so the force of the electric field. However, that just gives you these values. It doesn't really get us to the point of the end, because great, you can measure the voltage, you can measure distance, we can measure gravity, and therefore get E, but only if we know the mass of this particle. And the problem is, we can't measure the size of it because it's a drop. It's too tiny to measure with any exactness, so any certainty. The uncertainties are too big. So what he did instead was he turned off the electric field and he got them falling. Okay, so as they fell down, what happens is they're colliding with the air particles in the way, so these are a lot bigger than air particles. They're colliding with the air particles and they starts to develop drag. Okay, and that drag is basically the same size, and I'll say that on purpose, basically the same size as mg. Okay. However, as I've mentioned in lessons recently, there is another force, and that actually in the air, because this oil droplet is replacing that air, we've also got a little bit of upthrust. Okay, so he went into the detail, we can measure all these. So basically he's saying that the drag force, plus upthrust equals weight. Okay, so there's our fundamental inequilibrium forces. Is this always true? No. when it's at terminal velocity. So when it's not changing its motion, then he knows they're the same. Now, some exam boards ask you to do this proof. Even when they do, they don't include the upthrust. So this is a proper way of doing it, the fuller way. You'll find, I think you'll find it's not too bad. It may look messy for a while, just warn you. So he can work out the drag. He can work out to some extent. He can work out the upthrust to some extent, and he can work out the weight to some extent. But they all depend on the size of the falling object. So this is where Stokes' law comes in. So his drag is 6 pi nu rv. Now this is being found by dropping lots of different spheres of radius r through lots of different liquids. It's been proved over and over, or verified rather, over and over again with lots of different experiments. So he used the same mathematics of that as part of his drag. It has unknown r in at the moment. Velocity, he can measure that because these droplets as they drifted down was really quite slow because they are very small, they are very light. And so because of that, he could measure them with a grid of a vertical, I think it is. Biologists in the room, help me. But yeah, he measured a scale and he could measure the time it took to drop past that scale. So he had their velocity. So he has that. He has the stickiness, the viscosity of the air that it's falling through, and there we have a constant. So I need to add on my upthrust, which is the mass of the missing air, okay, times by its times by gravity, okay, which is equal to the weight of the oil times by gravity. So oil. Now, how do we get the mass? We know it's a spherical object, so we know that in generically language, rho equals mass over volume, and so if you want mass, it's going to be rho v. They're spherical, the spherical missing air and the spherical oil droplet that's filling that space, so that's going to be equal to rho times 4/3 pi r cubed on your data sheet on the mass page if you ever forget. So there's the volume of the sphere, density of it, that's where we get our mass, and if we want our weight, we multiply by g. Okay, so I'm going to substitute these into those two spots there. So this is where it will suddenly look a little bit messy. Don't you panic. Need a lot more space. So 6 pi nu rv plus, and let's multiply it out in a neater way. I'll move the rho to the end, I think. So we got 4/3 pi, excuse me, pi r cubed times by density of the air, okay, because it's the mass of the air that we're trying to find, multiplied by g, okay. And on the other side we have exactly the same but with the other density. So 4/3 pi r cubed rho oil g. Now looking through, we can simplify things a little bit straight away. We've got r, we got r, we got r. So let's get rid of some of that. We'll go to 2, and that gets rid of one of them. Okay, we have pi, so we can get rid of pi. That'll make it easier. And so we can start to simplify everything down. So what I've got is 6 nu v equals, makes mistakes, plus 4/3 r squared rho air, I'll just make it as an a now, multiplied by g equals 4/3 r squared rho oil g. Because they're the same, I'm going to simplify that. We will need to get rid of our r, so I'm going to take it out a little bit. We can take our 4/3 out as well, because that's the same. We could take a g out. So effectively, if I subtract all of that from this, or move this across, we have battery failing quickly. We've got 6 nu v equals 4/3 r squared g multiplied by air minus oil. And what I can do from that is I can get my radius from it, so I can use it for the mass and so on by rearranging this around. So I basically end up with 18 over 4 nu v. Bit inconvenient, so I'm going to move that out of the way, but we have our over g, excuse me, let's take the g across, and we have our subtraction of densities. Okay, so we know those, we can measure those on vast scale, we know what gravity is, we know what the stickiness, the nu is, and we can measure velocity, and that will give me r squared. So this process gives us the whole radius, and then from there we can find the mass to stick into our section over here, and all of that brings us down to this point. Okay, so tricky, but really straightforward in terms of adding up the forces. Okay, long way. For us, we want the idea that forces balance. Can we identify what forces, whether it's for dropping oil droplets or anything else? If they're stationary, then it's the electrostatic force upwards times by equal to the weight downwards. And the fact that, of course, if we're looking at parabolas, the maths of parabolas again looks complicated, but actually it's just s equals ut sideways, and it's acceleration towards or away from the plates, okay, to give you that parabola. So lots of thinking. What it actually comes down to is quite simple things. That's really useful. Okay, the forces are really useful. Our idea that we have some sort of particle and therefore we have some sort of force on it, etc. That's really useful. Okay, but in the end it's all about Newton's first, second laws.